Um, okay, so first of all, I would like to start with thanking the organizers for this beautiful summer. I learned a lot with talking with Gargi all this 8 weeks. Um, so what we studied was not something that I had in mind when we started this summer, uh, but Gargi uh, is from nicer India, and there she's going to start her 5th year, and she had a really clear picture of what she wanted to do, uh, which was in broad terms harmonic analysis. And I know very little about harmonic analysis, so we did something that could teach us both new things. So I really enjoyed it, and I want to thank organizers and also Gargi for this 8 weeks. Um, so I will just let her speak now.
Thank you, Oscar. I would first of all like to thank all the organizers of our TRP Turkey 2023 for organizing such a wonderful program. And obviously, I would like to thank Oscar for all the fun discussions and for guiding me throughout the last 2 months. So today I'll talk about amenability and Hochschild cohomology in Banach Algebras. So why did we choose this topic, first of all? So when we applied for the program, we both put representation theory as our interest, but it turned out later that we were interested in very different parts of representation theory. Gargi likes abstract harmonic analysis, in which we do calculus on groups in some sense, and Oscar likes module theory and homological algebra, which can be seen as a generalization of linear algebra. So we tried to find something in common, and we actually found something in common. So mathematician B.E. Johnson published a monograph in 1972 named Cohomology in Banach Algebras, in which he used homological algebraic tools to prove some theorems in the theory of Banach algebras, and it opened up a whole new field of research in mathematics. And this theorem is actually one of the first theorems that Johnson proved. So it says that let G be a locally compact group, then G is amenable if and only if H1 L1G, X star is trivial for every Banach L1G bimodule X. So our goal for this talk would be to explain what all the colored terms mean. So I've put them in colors because I don't know, I thought it might help all of us to remember these new terms till the end of this talk. So let's start. First, we have locally compact groups. So a topological group G is a group with a topology defined on it such that the group operation maps, the multiplication map and the inverse map are continuous. Continuous in the topological sense that inverse image of all open sets are open. And a locally compact topological group is a topological group whose underlying topology is Hausdorff and locally compact. That is, every point in X has a compact neighborhood K in G. Some examples are R, Q, C, C with plus. They are all additive groups, additive locally compact groups. Then Lie groups are locally compact because they are locally Euclidean. And then GL and R, the set of all invertible transformations from Rn to Rn is again locally compact because we can identify it with Rn square. Okay, then comes hard measure. So we, in some sense, want to do some calculus on groups. So for doing calculus, we need some measure because we want to do integration and all of that. So hard measure is something of that sort. A left hard measure on a locally compact group G is a left invariant Radon measure. So if you don't remember what Radon measure is, then no need to worry. We won't use it anywhere in this talk. The important thing is the left invariance of hard measure. It means that you can translate all the Borel sets in G to the left and its size would remain same. Similarly, we can define right hard measure, some measure that is right invariant. The right translations have same size all over G. And note that they coincide if G is commutative or abelian. Then there comes this theorem by Well and Haar, which actually confirms the existence of a non-zero left hard measure on any locally compact group G, and hence we can do all sorts of calculus and analysis on G. And it also says that it is unique up to a positive multiplicative constant. So that means whatever we do, that is well defined. Whatever we do on the group, that is actually well defined. For example, the n-dimensional Lebesgue measure dx is the Haar measure on Rn. So we call it the Haar measure because first of all, it's unique and Rn is commutative. So the left Haar measure is the right Haar measure. So there's no distinction. Okay, so the next term in Johnson's theorem was amenable groups. So why did amenable groups, how did amenable groups come? First of all, so the Banach paradox says that one can cut an apple into finitely many pieces and reassemble them to get a solid ball as large as the earth. So this is nonsense. So how can something of this sort can happen? So in some sense, some groups or some spaces have paradoxical decompositions. During his study on the Banach paradox, von Neumann introduced the notion of amenable groups using some measure theoretic terms. And later it was shown that amenable groups are precisely those groups which do not have any paradoxical decompositions. So in some sense, amenability is a nice property, as the English word says, that they're nice to work with and all of that. Later, many other equivalent definitions of amenability have been introduced, and one of which we will talk about in this talk in terms of Johnson's theorem. So let's define amenability using invariant means. Consider L infinity G, the space of all essentially bounded continuous functions in a locally compact group G, and we say a map from L infinity G to C is a mean. So it's basically a functional on L infinity G. So we'll call it a mean if m of the indicator function of G gives us 1 and m is also positive functional. Then m is called left invariant if m of phi G, if m of phi for all G in G, where the function phi G is just the left translation of the function phi. That is phi G takes input x and gives us output phi of gx. And a locally compact group G will be called amenable if there exists a left invariant mean on L infinity G. So here is a quick remark. It says that if G is amenable, then any closed subgroup H of G is also will also going to be amenable. So we'll use this remark in the next slide. So few examples of amenable groups. The first example and very important example is the class of compact groups. If we take mu to be the normalized left hard measure on a compact group G and define the functional on L infinity G by this equation, m of phi is the integration of phi with respect to the hard measure, then obviously m of the indicator function of G will give us 1 because the hard measure is normalized, and m is clearly left invariant mean because we're working with left hard measure, which takes care about left translations. So yeah, hence G is going to be amenable. The next very important non-example of amenable group is F2, the free group on 2 generators. So it lies actually at the very heart of Banach paradox. So this is very important. And using this, we can say that by the previous remark, any group containing a closed subgroup isomorphic to F2 is also going to be not amenable. One such non-example is SL2R. All the linear transformations, all the invertible linear transform, or all the invertible 2 cross 2 real matrices whose determinant is 1. So we can show that this subgroup H, which is generated by these two matrices A and B, is actually going to be isomorphic to F2 by the ping pong lemma. Okay. Okay, so next we have a very important theorem called as fixed point theorem. Some people also call it Markov-Kakutani fixed point theorem. It characterizes amenable groups in other terms. We'll see that. So, and it's also very important because we'll use it later in the proof of Johnson's theorem actually. So let X be a topological vector space and let G be a locally complete group. Then a continuous action of G on X is said to be an affine action if the map phi G, which takes X to Gx, is an affine map for all G and G. Okay, so this fixed point theorem says that for any topological group G, G will be amenable if and only if any continuous affine action of G on a non-empty compact convex subset X of a locally convex topological vector space has a fixed point. So it's a mouthful and there's a lot to remember, but you don't need to remember it actually. We'll come back to this theorem when we'll use it. But one of the immediate corollaries of this fixed point theorem is that every abelian topological group is amenable. I mean, as expected, because abelian groups are really nice, so they better be amenable. Okay, so amenability done. Next, we come to Banach algebras and Banach bimodules, which we also have seen in Johnson's theorem. So first of all, what is a Banach algebra? A Banach space over C is a complex vector space with a norm such that every Cauchy sequence converges, and a Banach algebra A is a Banach space equipped with a multiplication which is compatible with the vector space structure. That is, it's distributive over vector addition and is also compatible with scalar multiplications, such that this condition holds that the norm of x dot y is going to be less than equal to norm x norm y. One very important example that also appeared in the first theorem by Johnson is L1G. So what is L1G? It's the set of all functions f from G to C. So it's that integration of mod f with respect to the left hand measure is finite. And we take equivalence classes of all such functions where f is equivalent to G if and only if f is equal to G everywhere except on a measure 0 set. So this L1G becomes a Banach algebra with respect to the convolution product star given by this formula again. F star Gx is integration f of y, gy inverse x, d mu y. And we can also show that the L1 norm of f star G is less than equal to L1 norm of f into L1 norm of G. So that makes L1G into a Banach algebra. Then, now that we're done with Banach algebra, let's come to Banach bimodules. So let A be a Banach algebra and X be a Banach space such that X is an A bimodule algebraically. So that means there's a left action and a right action of A on X, which also satisfies the module conditions. The next is called a Banach A bimodule if again the non-compatibility holds that norm of A dot X and norm of X dot A will be less than equal to norm A, norm X. So what are some examples? So we'll actually construct a new example from a given X, from a given Banach A bimodule X. We consider the dual of X, the space of all linear bounded functionals on X. Then X star becomes a Banach A bimodule in a natural way. The module maps are given here where A comma F goes to the functional AF, which takes X to FXA, and F comma A goes to FA, which takes X to F of AX. And it's also easy to show that actually so X star is a Banach space with respect to the operator norm, and we can show that the operator norm of AF is less than equal to norm A, norm F, and same for the other direction. So indeed, indeed X star becomes a Banach A bimodule if X is a Banach A bimodule. Okay. So next I come to what is H1AX or the first Hochschild cohomology group. So let's first talk about derivation and peanut derivation. So derivation from a Banach algebra A to a Banach A bimodule X is a bounded linear map T such that this condition holds. DAB is equal to A dot DB plus DA dot B. So notice that here these dots are the module actions of A on X, because DB is an element of X, A is an element of A. So we're multiplying from left and again from right. And note that this is in a sense a generalization of the multiplication rule of differentiation, which is also known as the Leibniz rule. And for example, fix some x in X and consider the map Ix from A to X by Ix A is equal to A dot X minus X dot A. We can show that Ix is a derivation, which means Ixab is equal to A dot Ixb plus Ixa dot B. So this is going to be a derivation. All such derivations are called linear. Okay, then here are a few notations. So the set of all derivations from A to X will be denoted by C1AX, and the set of all linear derivations from A to X will be denoted by B1AX. So here is one simple thing to note, that both this C1 and B1 are actually subspaces of the set of all linear operators from A to X, which is a Banach space in the operator norm. So if not anything else, this Z1 and B1 has a vector space structure, because Banach spaces are first of all vector spaces. So they have a vector space structure, so we can talk about quotients and all of that. And that is exactly how we define the first Hochschild cohomology. So H1AX is defined as the quotient of C1AX by B1AX, and it's called the first Hochschild cohomologic group of A with coefficients in X. Okay, here are a few remarks. This definition is a consequence of a more general homological construction called the Hochschild chain complex and the Hochschild of cohomology, which we also studied during this program. And higher Hochschild cohomology groups for n greater than equal to 2 also exist. So you look at the chain complex, you look at the co-boundary maps delta n, and you look at their images and kernels, like the co-cycles and co-boundaries, and you can show that actually delta n composed with delta n minus 1 gives us 0. So the images will be subset of the kernel, so you can take quotients and all of that, and at each stage you take the quotient and you define it to be the nth Hochschild cohomology. But we won't go into all of that right now. Okay, so again, we have come back to Johnson's theorem. G is a locally compact group, then G is amenable if and only if the first Hochschild cohomology group of L1G with coefficients in X star vanishes for every Banach L1G bimodule X. In other words, G is amenable if and only if every derivation from L1G to any dual Banach L1G bimodule X star is actually going to be linear. So I have removed all the colors because you have understood everything now, and we're back to black and white and life is dull and blah, blah, blah. But we actually don't understand everything. As always, we still have to go through the proof of Johnson's theorem. So here is an outline. It's actually a very long proof, almost 3-4 pages long, and requires lots of propositions and definitions and all of that. So we have managed to put all of this into 5 points. So let's see. So we'll only present the proof of 1 implies 2 here. So first of all, we do some reduction of the problem. So instead of looking at any Banach L1G bimodule X, we look at a subclass of Banach L1G bimodules, which is known as pseudo-unital. So they have some nice properties, so we can use that in the proof. And then we extend any derivation from L1G to X star to a bigger space called the measure algebra MG, which is, L1G is a subset of MG, so we can extend D to D tilde on MG, and this is also going to be a derivation on MG. and d tilde will be continuous with respect to the topologies on mg and x star and all of that. We can prove that. And then consider K to be the weak star closed convex hull of some elements in X star. So what are these elements? These elements are something that we get from the module action of Mg on image of D tilde. So image of D tilde is a subset of X star and it's a Banach Mg module. So we can talk about module action. So everything is nice here. Then K is convex, obviously, because by definition, it's a convex hull of something, and it's also weak star compact because Banach Algebras theorem says that any closed unit disk in X star is actually weak star compact. So K is going to be weak star compact. Now, the idea is to construct an action of G on K such that the existence of a fixed point of this action would imply the inertness of D tilde. Now, as soon as we hear fixed point, this implies that we'll have to use this fixed point at some point. So it is actually possible to construct an action which in addition is also affine and continuous. Since it is amenable by Day's fixed point theorem, it will have a fixed point. So let's go back to Day's fixed point theorem. What does it say? G amenable if and only if any continuous affine action of G on a non-empty compact convex subset X of a locally convex topological vector space has a fixed point. So here K is our K, which we defined as the fixed closure of convex hull of something. That is, we showed that it's convex and it's compact, it's non-empty. And if we define the action of G on K to be affine and continuous, then since G is amenable, we'll have a fixed point. And by part 3 of this proof, this will imply D tilde is actually inner, and then since D tilde is just the extension of D, it would imply that D is also going to be an inner derivation. Okay, so in light of Johnson's theorem, we can define amenability for arbitrary Banach algebras in a similar way. So how do we do it? A Banach algebra is called amenable if the first Hochschild cohomologic group of A with coefficients in X star is trivial for every Banach A by module X. And that's all. This is us in our last meeting. And thank you all for your attention.
Okay, thank you, Gargi, for the